So here is Unit 9, Day 2, Graphs of Zeros of a Polynomial. So today we're going to kind of connect that whole idea of a power function and the shape of graphs and how they behave with writing equations for graphs. And we're going to start off mainly with focus on the roots. So first thing that we need to talk about is, just briefly, polynomial functions are used to represent real-life situations and are written in the form coefficient times a variable plus coefficient times a variable plus coefficient times a variable. This is really just a fancy way of writing things like x squared minus 2x minus 8. This is just creating the opportunity to interchange different coefficients. So like maybe this one is 7, and this one is 6, and this one is 8, and this one is -2. So don't get hung up on that. You will not be required to memorize that. Just know that this is just a way of writing things out so that things can be interchanged, right? You can change the value of the coefficient, and it can still be a polynomial function. All coefficients, aka all the a's, are real numbers. All the exponents in a polynomial function are positive, so no negatives. There are no breaks or interruptions in the graph. It's what we call a continuous graph, right? You can graph it from one end to the other without picking up your pencil. They have distinct rates of change. So if I pick from here to here, it will have a distinct average rate of change. If I pick from here to there, it will have a different average rate of change. The end behaviors always approach infinity. So every time we put these arrows on them, basically just means they're continuing on forever. So let's go over some basics real quick of just your standard polynomial. If I'm given f of x equals x squared minus 2x minus 8, and I just asked you to factor that, well, the first thing you would do is replace f of x with 0, because f of x is just y, right? So y here equals 0, so we have 0 equals x squared minus 2x minus 8. And then we say, okay, 1 times -8 is -8, and the sum is -2. So two things that multiply together to give me -8, but add to give me -2 are -4 and +2. Now, because this coefficient is 1, we can go straight to the factors, x plus 2 and x minus 4. And then I can solve for the roots, where I set each factor equal to 0. So here, -2 equals x, and x minus 4 equals 0. So here, x equals 4. We can go over to my graph. X equals, don't fall. X equals -2, 1, 2. When y equals 0, right? Whenever you solve for these roots, don't forget that this really means -2, 0. And this really means 4, 0. They always correlate to the graph. So here, this is -2, 0, and this is +4, 0. Okay. Also, to get my y-intercept when I want to graph the function, really you only have to look at this last number, because your y-intercept is when x equals 0. So if x equals 0, this is 0 squared minus 2 times 0 minus 8. So 0 minus 0 minus 8 is -8. So -8 is our y-intercept. Okay? And just to make sure on Desmos that we've got it all correct, let's add it in there. Y equals x squared minus 2x minus 8. Okay, and here's our graph. And we have -2 and 4. Intercept is 0, -8, and 1, -9. That'll just make our turning point that much easier to graph here. I always recommend that you guys, you have the opportunity at home to go ahead and just throw it in Desmos. And starting at negative infinity, that's what that arrow means, going all the way to positive infinity. Okay, so there's your graph. Well, here's the thing. What the vertex, let's just go through the questions real quick. That's 1, -9. That was easy to find on the Desmos graph. The zeros are -2 and 4. That came from factors with the opposite signs. So this came from x plus 2. This came from x minus 4. So if I just gave you this graph and said, what is the factored form of this graph, you could say y equals, well, this is -2, and this is +4. You could say that x plus 2 times x minus 4, right? Because that's where those factors came from, right? This is what we call the factored form. And you can write that direct from the graph as long as it doesn't have a value out front right here. Okay, so let's start to get into, one more thing, the end behavior of this graph. Well, it's an even power, so it should be going in the same direction, right? Even power. Same direction. And it's a positive x squared, which means it's going to both ends to positive infinity. Okay, so from there, we talk about more behaviors of graphs. So the first thing that I want to do with this one, if I'm given an equation and I have my Desmos handy, I want you to pull it up on Desmos. So we just graph this one, take that one off, and here's this graph. Okay, so I've graphed this function here. The first thing that we want to look at is how many turning points does it have? It has 1. That makes sense, right? Because this is an even function. An even function has to have its end behavior go in the same direction. Same direction. Okay? And that direction will be negative. So when I graph it, it will be negative. Now, I don't foresee you having to do this, but I wanted to show you how it affects the graph and how you would handle it if you did see it. So if it has a negative out here, we're not used to graph or factoring with negatives out front. You can factor that negative out of the entire function. So we could actually rewrite f of x as negative x squared, and you have to factor it out of every single sign. So if this is positive, that becomes negative, and this becomes positive. Then I can factor what's in here. Two things that multiply together to give me +10 but add to give me -7. Well, since my coefficient is 1, that's just x minus 5 and x minus 2. Going straight from this factored form, I know, first of all, it's an even function, so the end behavior is in the same direction. This negative means it's upside down. And it has a root of the opposite of what's inside the factor. So that means that x equals 5 and x equals 2. So it's an upside down parabola that has 2 roots at 5 and 2. So I can go straight over here to my graph at 5, 1, 2, 3, 4, 5, and 2, 1, 2. Okay, and I'm when I go to my graph here, I can see that my turning point is like right here. Come on. At 3.5, 2 1/4. So good estimate here. 3.5, 2 1/4. Right? Doesn't have to be perfect. You guys won't be graphing anything by hand anyway, so don't worry. And it looks like that. Okay? So that's what happens when we have a negative symbol out front. But I can easily identify what the roots are just by looking at the factors. Well, if I can easily identify what the roots are by looking at the factors, that means I can write factored forms of equations given just the graph. So I want to start thinking about a couple of things. What's the power on this? Well, the end behavior is going in opposite directions, which means it's an odd power. Okay? And the number of turning points will help me determine what that power is. So it has 1, 2 turning points, which means most likely it's a power of 3. It also has 1, 2, 3 roots, which tells me it has 3 factors. So the first thing I want to do is write y equals, or f of x equals, either doesn't matter. And then identify what these roots are. So if this is -1, right, the x value is -1, that means that there's a factor here that is x plus 1. And if I have a root here that's 2, that means there's a factor that directly correlates that's -2. It's essentially the opposite sign. And if this root here is 3, then I'm going to have a factor of x minus 3. Okay? And I also can check, too, to make sure that I'm right. This guy right here, the y-intercept, if I were to multiply 1, 2, and 3, right? 1, excuse me, I should have said -2 and -3. That is +6. Notice that this is 0, 6. So when you do that, you will know you're on the right track. This is the factored form of this polynomial. If they ask you specifically for standard form, you have to multiply it out. I don't believe that that's in the delta math at all. Anyway, I don't think it's necessary at this point. You guys know how to multiply. So let's do some more, because there's more characteristics to consider. So again, we have end behavior. It's going in opposite directions. Okay, so that means it's odd. The only thing though is like in this last one, we started at -infinity and we ended up in +infinity, and we essentially had a positive function. Well, here, this is starting at +infinity and going to -infinity. That means we're going to end up with a negative function. So f of x equals negative. Why? Because it's flipped upside down. Then we want to identify the roots. It's an odd, and the turning points help me to determine, well, there's 1, 2 turning points, so this is a cubic function. So if you have 2 turning points, you have a 3rd degree polynomial. When you have 1 turning point, you have a 2-degree polynomial. Okay, so it's always 1 more than the number of turning points. That means I can expect 1, 2, 3 factors, right? It's a cubic, which means I'm going to have 3 factors. So I'm just going to write the roots here. There are -1, that's a root, which means the factor that directly corresponds is x plus 1. And here I have a root of 2x minus 2. If this is +2, this is -2. And if this is positive 3, this is negative 3. And because it's upside down, the entire thing will be negative. And when I say upside down one more time, this just means that it starts at positive infinity and goes to negative infinity. Okay? So what happens when we have a polynomial that has end behavior that goes in both directions, which means it's even, right? It's an even powered polynomial. It has I should say both directions, it's even, and that's both directions are going up. So that means it's also a positive one. So we don't have to bother about putting in the negative. So f of x equals, the number of turning points is 1, 2, 3. So it's a 4th degree polynomial. So 1, 2, 3, 4. Okay? So here I have 0. So that means x plus or minus 0. You could just write x, or x minus 0. Doesn't really matter. You could just write x. It's totally fine. Negative 1, which means negative 1 means x plus 1. Negative 2 means x plus 2. And negative 4 means x plus 4. Okay, and just so you can see that a little clearer without the arrow in there, that's x plus 1, x plus 2, x plus 4, and that's f of x. Okay, so this is the factored form, or identifying the roots of this particular polynomial. Now, there are one more thing that we have to talk about, and it's what happens when you have repeating roots, right? If you've got a 4th degree polynomial, right, is it possible that this root and this root could be the same? Well, let's see. Well, this right here, okay, first let's talk about the end behavior. That helps us to determine what really is the scope of material we need to figure out here. The end behavior is that it is opposite directions, so it's odd. It starts at negative infinity and goes to positive infinity, which means it's also a positive odd function, meaning that the coefficient out front is positive. It also has this. I still keep jumping ahead, I'm sorry. Turning points. There are 1, 2 turning points, and that means it's a 3rd degree polynomial. So y equals 1, 2, 3. Now, here's the thing. I've got negative 1, that's a standard root, right? That goes straight through the x-axis, and it goes from one side to the other. Done. That's a root, x plus 1. However, this guy right here, I finally get to talk about him. This is what we call a tangent root, okay? And whenever you have what we call a double root, that's what happens on the graph. So if I have x here equals 2, 0, that means that I not only have that 2, x minus 2, I have 2 of them, x minus 2. And we will commonly write that as y equals x plus 1, and we'll condense that so it's x minus 2 squared. Okay? So whenever you see a squared in an equation like that on a root, or on a factor, excuse me, that means that it's a tangent root or a double root. Okay? So that's how that works. And last one, just to make sure. So the first thing we want to look at here is end behavior. And we say, okay, if the end behavior is going in the same direction, that means even. We also notice that that same direction is positive infinity, which means this is a positive even power. Okay? Then we look at the turning points, and we say it has 1, 2, 3 turning points, meaning it's a 4th degree polynomial. So here I should expect 1, 2, 3, 4. Now, I have the only two spots that I have hitting the axis are -2 and +1. Well, here you notice, first of all, we need 4 total roots. I have 2. But the behavior at the root is telling me that this is a double root because this is tangent. Okay, that is a tangent double root. Okay, so if it's -2, this is x plus 2, x plus 2. We double that root. The same thing with x equals 1. You get x minus 1, but it too is also a double root because its behavior on the graph is tangent. So this is not only x minus 1, but x minus 1. And you will commonly see that written as y equals x plus 2 squared, x minus 1 squared.